Okay, so for today's Cut Enough seminar, we're very happy to have Aaron joining us from Cornell. Aaron is a PhD student in Cornell in Una Kim's group and has done some really interesting work on dualities and hydrodynamics. And today he's going to tell us about going beyond Ohm's law, Bernoulli effect, and streaming in electron hydrodynamics.
Great. Thanks a lot for the invitation to speak and just to join you guys on Zoom. Unfortunately, not in person, but I guess such is the times these days. So this is work that I've been doing in collaboration with Sam, at least on the first paper, and also Vadim Oganessian over at CUNY and my advisor, Una. And you can find the papers referenced here. Feel free to interrupt at any point. Just ask any questions that you might have. Right. So when we talk about transport in condensed matter, we traditionally divide up the different regimes of transport based on the shortest length scale that is present in the problem. So perhaps the most common one we think of is when the electron impurity length scale is the shortest, which is known as the diffusive regime, where you have some carrier just going around executing a random walk as it bounces off impurities that are present in the sample. So this is your typical ohmic resistor type of material. Another very common transport regime is known as the ballistic regime, where the electron boundary scattering is dominant, and you have the particle bouncing primarily off of the walls of the sample, say, in 1D wires and things like that. And so the regime that we're particularly interested in is when the electron-electron scattering length is the shortest length scale that is present in the problem. And so here you see that this is a regime characterized by strong interactions, lots of collisions between these particles. And in particular, kind of from a practical material standpoint, this requires your material to be ultra clean to remove the presence of impurities and things like this. So this strongly correlated hydrodynamic regime has been of interest for many decades in the condensed matter community. And there's a long history of electron hydrodynamics. So here's just a few selection of papers that just demonstrating that people have tried to study hydrodynamics in this framework as a way to understand strongly correlated phenomena. And I guess in the early days of hydrodynamics, people looked at primarily local transport quantities, such as DC conductivity, thermal conductivity, Wiedemann-Franz ratios, and things of that nature. More recently, theorists have been looking at viscous signatures of hydrodynamics, which lead instead to non-local transport behavior. We experience this in our everyday lives. Say when you pour out honey from a jar, you're immediately struck with the viscous flow resistance as trying to get it out. Or you see large-scale vortical structures such as behind this airfoil here. And now, what has made this field particularly exciting and interesting in recent days is the fact that some of these non-local effects have been observed in experimental settings. So for instance, in Hall bar geometries where you inject current and measure this voltage as a result in kind of this non-local fashion, you measure, the people have measured negative resistances, which is a signature of current backflow, and the fact that there are vortices that are forming inside of this Hall bar geometry. In addition, if you look at the resistivity of these hydrodynamic materials against the channel width, you'd expect a linear or a 1 over W type a functional dependence of the resistivity for a typical ohmic conductor, but instead the data shows something else, something closer to 1 over w squared, which is a signature perhaps of viscous flow. And then more recently, there have been some exciting experiments that have tried to directly measure the flow profile in these channel type geometries, measure the positional dependence of the current flow. And you see these parabolic type structures, which is very reminiscent of Poiseuille type flow and viscous flow. So the theory that that undergirds all of these experimental results is quite simple, actually, and it's just written here, this not linearized Navier-Stokes equation. And the reason why it's so simple is because this linearization, just meaning linearized in velocities or currents, just throws out a lot of the complications with Navier-Stokes. You're left with two terms here. So one, you have the electric field, which is the analog of the pressure gradient. And then you have this del squared J corresponding to the shear viscosity. And now there's one additional term that you add to make it electron hydrodynamics, which is the scattering rate gamma added by hand to mock up the fact that in any realistic system, you need to have some finite resistivity in the sample. Okay, and so by solving this equation, you can reproduce these vortical structures, this channel width dependence, and the Poiseuille type profiles. And so for convenience, instead of working in this language, we'd like to invert it to talk about conductivities at long wavelengths. So you have the sigma naught corresponding to the scattering rate gamma, and then the sigma 2 corresponding to the viscosity nu. And as you can see, the sigma 2 corresponds to some q squared component of a conductivity. Now, if you stare at either of these two equations, you'll find that there's a natural length scale that emerges in this equation, namely the ratio of nu to gamma, or sigma 2 to sigma naught, which we call the viscosity length scale RD. And what this length scale does is it tells you about the strength of viscous effects, as it's named. So for instance, if I take a channel geometry of width W and look at the shape of the current profile, for small RD compared to the W, I'll get this rectangular plugged flow profile, which is characterized as ohmic behavior, whereas for large RD, you'll recover the Poiseuille flow, the parabolic Poiseuille flow profile. And similarly, if in these injection profiles, injection geometries where you start generating these vortical patterns, this viscosity length scale RD is what sets the size of the radius of the vortex. Now, so the generative equation of motion is written here, coming from Navier-Stokes hydrodynamics. But if you take a step back and kind of forget how you got to this equation, this is really nothing more than a statement of Ohm's law. Okay. And with a momentum dependent conductivity sigma 2. And because it's just Ohm's law, you kind of have to ask the question, whether or not this viscosity or this sigma 2 implies hydrodynamics. We've kind of shown the other way around, that hydrodynamics gives you this equation, right? So, thinking back on these non-local transport experiments, does seeing all of these interesting non-local behavior really mean you're in a strongly interacting electron-electron collision length, very short hydrodynamic regime? And so this was one of the questions we asked in this first paper, where we said, okay, let's try to understand the origin of viscosity and the origin of sigma 2 in a microscopic fashion. Okay, so to take the simplest model we can think of, which is we just take free fermions, this H kinetic term, and we're going to consider a disordered free fermion model. So you just have typical Gaussian disorder here, 0 temperature. And so this is a model without interactions and is definitely not going to be in the hydrodynamic regime ever. So, do the standard thing where you go forward and calculate the conductivity of this through some Kubo formula, evaluating diagrams of a type like this, where you're inputting some finite momentum. Okay. Now, this is, standard typical textbook type calculation with the one additional wrinkle that, typically you stop at sigma naught. You just have to we have to calculate to subleading order to get a sigma 2. That raises some calculational challenges and actually makes this problem, as far as we know, we're the first ones to actually do this in 2+1D. If any of you know of another reference that does this, please let me know. But the only other reference that we could find is in this Liu Annals of Physics 1970, pretty old, in a 3+1D setting. So just due to some technical challenges, we're just going to go ahead and evaluate these integrals numerically and see what you get out of evaluating this conductivity to second order. So, so here I've plotted the viscous length scale against the density, the carrier density with some normalization prefactors. And I guess the immediate thing that you see is that RD is non-zero. Right? You have a non-zero viscous length scale, implying that you have non-local transport behavior, even though this is a completely disordered, completely non-interacting model. And so to kind of understand why you would have a non-zero RD, you can kind of understand this numerical result through a simple dimensional analysis type argument. Namely, if RD is some length scale in my problem, let me just write down through dimensional analysis means the parameters to give me some length. Okay, so you have a Fermi velocity in the system, and then you have some scattering rate gamma, right? Now, in this particular model, we're taking the dispersion to be k squared over 2m, where we note that the density of states is constant in 2+1D. So, sorry, constant as far as the density goes. So then the Fermi velocity will go as the square root of the density, giving you this nice square root behavior. And so this simple dimensional analysis argument reproduces these features. And what this tells you is that this viscous length scale is really just a measure of the electron impurity length scale. And so as a result, we find that length scales other than just electron-electron scattering can contribute to sigma 2 to RD to some of these non-local transport features. And so this kind of raises the bar for really determining from these non-local transport experiments if you're really in a hydrodynamic regime or not. You need to really turn other knobs such as temperature, magnetic field, electron density, understand how the microscopics of those go, and distinguish which one's electron-electron scattering, which one's electron impurity, electron phonon, et cetera, et cetera. So rather than go into all of the nitty-gritty of the microscopics of this, we decided to take a step back and kind of ask a higher level question, which is Navier-Stokes and hydrodynamics are very rich phenomena, exhibit very rich phenomena, and should be very distinct from Ohm's law behavior. And therefore, there must be phenomena that reside in this Navier-Stokes type description that would be very distinct from typical Ohm's law. So to see this, let's just turn to the full Navier-Stokes equation. Unfortunately, it kind of involved, but so here we have on the left just momentum balance. On the left we have some dp dt, and then on the right is just all the collection of forces. Right, this is just a momentum balance equation. So the one interesting feature, which will be the primary player for us for the purposes of this talk, is this convection term, right? Which is nonlinear with the power of 2 velocities, and this term by itself puts you outside of Ohm's law. And the reason why you have this term is because you have velocities of field, and so you need to account for momentum fluxes through control volumes. It's not simply the partial derivative of momentum with respect to time. On the right-hand side, you'll have all the forces. The terms in gray are the ones that are typical in a Navier-Stokes description. You have a pressure term, then you have these compressional and shear dissipation terms, or if you like, the shear and the bulk viscosity terms. And then you also have these terms in green, which are those terms that you add to make this electron hydrodynamics. Namely, the carriers are charged, so you have some electric force, and then you have some resistivity, as I mentioned earlier. So it'll be useful for us to think about this convection term as some kind of effective force that is being set up by gradients of velocity. And we'll unpack this more as we go forward. So those of you who have had some more exposure to fluid mechanics may know that the nonlinearities in the Navier-Stokes equations are typically characterized by what's known as a Reynolds number, where at high Reynolds numbers you start going into regimes of turbulence. And so the Reynolds number that you typically know is defined in the following way. You take the convective force and take the ratio of that with the force associated with shear viscosity. And of course, this expression here on the left is pretty complicated if you have some actual velocity with position dependence and all of that. So what people really do is you take some dimensional estimates of this and then just estimate kind of a back of the envelope calculation to give you some measure of the strength of the nonlinearities that are present in the system. Okay. And then here I just written it also for in terms of currents instead of velocities. So we're not. I mean, it would be very interesting and very nice if we could go to large Reynolds numbers, say even Reynolds numbers greater than 1. But in the electron hydrodynamic systems as they are right now, that's pretty tall order. You'll probably end up melting your device by trying to drive currents that large. But so we're primarily interested in perturbatively small Reynolds numbers, say like 1/1000. And even there, we're going to see some interesting nonlinear effects. Now, this is I've discussed to you the typical Reynolds number, which is the ratio with the shear viscosity. But since this in this electron hydrodynamic setting, there's another dimensionless parameter that is important to keep track of, and which we call RE sub gamma, a momentum relaxing Reynolds number, where you take instead the ratio of the convective force with the resistivity here, and again do the dimensional analysis. And so, for if you want strong nonlinearities, you really need both of these Reynolds numbers to be large. So which one of these Reynolds numbers actually controls the physics in your system? You can just take the ratio of these, and this is related to this viscous length scale that we discussed earlier. Now, because in physical systems, as far as we know right now, say for this viscous length scale is going to be on the order of 1 micrometer. So this is taken from graphene. If we consider micron-sized devices, say 5, 10 micrometers, the momentum relaxing Reynolds number Re gamma will actually be the one that tends to dominate. In other words, it'll be the smaller one. And what this means is that viscous effects, terms that the effects due to the shear viscosity will tend to be suppressed, and really you only need to care about the comparison between this convection and the resistivity. And this is kind of, I guess, the reverse of how we have been thinking about hydrodynamics, where viscosity is, with viscosity as the major player and gamma is kind of this artifact that we want to get rid of. Okay.
Question?
Yeah, go ahead.
So since you're in a regime where momentum relaxation is kind of dominant,
yes.
Shouldn't you allow for more general nonlinear terms that aren't fixed by symmetries?
I mean, yeah, sure. That's yeah. So in general, there will, like, say if yeah, I mean, yeah, you're right. You would have so even I guess maybe one thing I should mention here is that we have these quadratic nonlinearities, which in the velocity, which in some sense are the lowest order. You, in principle, say from the lattice, the band structure, etc., you could imagine generating other types of dissipative v squared types corrections, v cubed, etc., which would also contribute. And I guess another thing is that there are nonlinearities that come because the density is not necessarily a constant. So technically speaking, if there's going to be nonlinear contributions from like rho times v and things like this as well. But yeah, you're completely right. Yeah, but for simplicity, we're just going to keep it at just at this level. Any other questions? All right. Right. So I guess now we can turn to some of these nonlinear effects that I've been promising to tell you about. And so all of these nonlinear effects are, at least the ones that we're talking about, are based in some kind of classical analogy. The first one being the Bernoulli effect, probably the most classic and prototypical example of convective acceleration. So if you've ever played with a hose or a faucet, you know that if you cover the hose with your finger, water will spew out at an increased rate because you need to conserve mass flow rate. So this constriction geometry is known as the Venturi geometry, or Venturi tube, as shown here. And if you not only keep track of the velocity as you go into the constriction region, but also of the pressure, you'll find that as the velocity increases, the pressure decreases. And this is a result of the conservation of energy, or also called the Bernoulli's law. And this, I want to point out that you can get this Bernoulli's law from integrating the Navier-Stokes equation, where this kinetic energy is coming directly from the convective acceleration term. This is all well and good, and it's a pretty innocuous statement. But if you translate all of these things to electronic language, imagine you make some kind of wedge with contacts on the edge, apply some voltage, measure the current, and look at the IV characteristic. What this Bernoulli's law equation tells you is that you get that voltage goes as current squared, or that the current goes as the square root of voltage. So what this means is that hydrodynamics immediately gives you a nonlinear IV, which is kind of interesting. So you can go ahead. So we can go ahead and solve the Navier-Stokes equations in this kind of wedge geometry. So here, for simplicity, we're just going to neglect viscosity for the same reasons we mentioned earlier, that viscosity is not going to play a major role. And then we're going to assume, make an ansatz that our flow profile is completely radial. There's no angular dependence in it. And you get the following result. So you'll have a linear term corresponding to the Drude resistivity, which is present when there's no convection. And then you'll get a Bernoulli contribution to the voltage, which is exactly what you would get if you had no resistivity. These terms just turn out to nicely add. And the IV characteristic is going to be this tilted parabola. So this blue curve is going to be our the stable branch of the solution, as it this is the linear response one going through the origin, and then you're going to have this gray dash one corresponding to some unstable solution. And then below some critical V naught, our ansatz just breaks down. And so what's happening in this regime of strong negative V naught is that my carriers are traveling strongly outward. And it's known in the fluid mechanics literature, if that you have a strongly divergent outward flow, that you'll start developing instabilities towards turbulence. So that's what's going on here. So what we're proposing is to look for this nonlinear term. Right? There are two kind of functional features that make looking for this term, as opposed to other nonlinearities, as Luca kind of mentioned, hopefully a little bit easier. Namely, that this Bernoulli term is very geometric in nature. It only depends on the input and the output channel widths, H0 and H1, and actually doesn't care at all about how long this wedge is. Kind of reminiscent of ballistic type transport behavior. Another nice feature of this is the fact that there's a factor of charge density in the Bernoulli term compared to the Drude term. And so if I imagine, say, in a graphene system where I can tune the chemical potential to move between from electrons to holes and change the sign of this carrier density, I can actually flip the sign of the Bernoulli term. And so for playing around with different devices and the gate tuning, one would hope to be able to measure and isolate this Bernoulli contribution to the IV characteristic. So to get a sense of actual numbers for graphene, here I have just run a PDE with the viscosity and everything put back in with the graphene parameters. We're taking device lengths on the order of 10 micrometers or so. And here I've plotted IV characteristic in the inset, and then the symmetric current fraction defined here as a measure of the nonlinearity against the total current. And as promised, the numerical data matches very, very well with this analytical result where we've neglected viscosity because RD is small compared to these lengths. So what you get at the end of the day is you expect symmetric current deviations about, say, 400 nanoamps if you have a total current about 200 microamps, corresponding to Reynolds numbers of about 1/1000. All right. Yeah. Are there any questions on this Bernoulli effect stuff? right. Okay, so the next effect that I want to discuss is known as Eckart streaming. And so here I have a nice video of the classical situation where on the left here I have some ultrasound transducer and then some glycerol solution where you see as this ultrasound transducer is turned on and just vibrating back and forth symmetrically, and you actually end up generating this jet of fluid flow, and which strikingly breaks parity here. And so one can imagine doing a similar type of experiment in the electronic setting, where you take some Hall bar type geometry and drive the left contact with some oscillating voltage, and then measure and look for some resultant DC current in my hydrodynamic material. So to make life easier for ourselves and simpler, we're going to gate this device to screen the Coulomb interaction to make sure that our hydrodynamic modes are as close to acoustic as possible. So to understand why you would get this effect, where it comes from, as this is a DC rectification effect, some kind of frequency conversion effect, we usually think of these perturbatively. So you imagine this oscillating voltage will drive some kind of oscillating current wave through my device. But here we have some traveling wave solution at leading order. But not only will it travel through my device, because of resistivity, because of viscosity, various bulk dissipation mechanisms, this wave will actually attenuate as it travels. There are also, of course, dissipation elements from the boundary of the device, say from a no-slip boundary condition. But for simplicity, we're just going to ignore those contributions, and we'll come back to them later. If you like, this is equivalent to taking a stress-free boundary condition. So if you take this leading order solution and then solve in an iterative way for the second order velocity, one term that you'll need to calculate is this second order convection force, which is a result of the first order velocity field that you had. And what you find that is that upon time averaging v dot grad v, this convective force is actually non-zero, and it depends on the strength of alpha of the dissipation that we had earlier. And therefore, this DC convective force is what's pushing along these electrons, providing this current and providing some kind of DC current flow, even though you had oscillating symmetric drive. Now, there's a very analogous situation where you apply some kind of oscillating voltage or oscillating E field and get some kind of DC current, and that is a solar cell. So in some sense, you can think about this device if this input voltage comes from some kind of laser spot or light spot as some kind of hydrodynamic solar cell, where as opposed to say a typical PN junction solar cell, where the reason why you have a DC photocurrent and parity breaking is the explicit construction of the P and the N side. What's breaking parity here is not the material itself, but the fact that I have asymmetric boundary conditions, namely I'm driving preferentially on the left with a voltage and grounding the right, and the fact that there is attenuation in my sample. So that's what makes the left to right asymmetry here. Okay. So beyond just the striking, visualizing this generation of DC current would be pretty striking in these hydrodynamic materials. So we can go ahead and try to understand a little bit more about functional forms and how strong this effect is. So here I've plotted the DC current against inverse length schematically. And so we find that at long device lengths, the DC current will go as 1 over L. And so this is typical for a typical resistor. And so you can kind of think of the DC convective force as providing some kind of effective voltage instead, if you like. At short lengths, you have to worry about a reflected wave component from the opposite contact, and which is why you're getting these interference oscillations. So to estimate this effect in graphene, for a length of about 50 micrometers, putting us in this long device regime, and frequency about 1 terahertz, you'll get a DC current about 1 nanoamp for about 24 microamps of input current amplitude. And so just to emphasize that, this interference regime is probably pretty difficult to reach. If you take a shorter device of 20 micrometers and look at here DC current against frequency, we find that the frequency oscillations are about, say, 2-3% at best of the total DC current, putting it at tens of picoamps for 1 nanoamp of DC current. So it's going to be pretty difficult to measure the interference effects. Okay. So before I move on from Eckart streaming, are there any questions on this?
So here experimentally, you're thinking of actually shining light on one side of the sample?
Mm-hmm. Well, right. I mean, it's a little, you have to be a little bit careful, I think. So in this, yeah, at a high level, yes, shining light in some sense, like putting some terahertz radiation on one side. I think one of the potential challenges is that terahertz radiation in vacuum is on the same kind of order as these device sizes. So designing the contact here to actually designing the laser spot and the contact here to actually receive on one side may be a bit of a challenge, but that's the general idea.
Okay, I see. Thanks.
May I ask a question?
Mm-hmm.
So if I think in this quasi-static limit with very long wavelengths,
yeah,
would I be able to look at this problem using the fact that the potential itself is not physical quantity? What is physical is the potential difference.
Mm-hmm.
And if I think about it this way, then I don't see the way to drive this system is actually breaking the parity, because I could equally well decide that the grounding point is actually the left side, and I drive the right side.
Okay. So what you're so if I'm understanding you correctly, you want to essentially make this k very, very, well, k is 1 over length, so essentially make the wavelength of this thing very, very long.
Much bigger than the size of the sample. So I'm in the regime where on the left, on the next.
Yeah. So I guess one thing that I haven't, I kind of skimmed over this, and this is why I put the frequencies at 1 terahertz. Of course, as you mentioned, if the frequencies are going to be really low, it's going to be some static limit, and in that case, this is what this grayed out region is here for, is the fact that there are other essentially you have to account for screening, charge screening in the device, and this will essentially kill the effect if your frequency is too small. Because how do I want to explain? How do I want to explain this? Basically, if I have a right, so if I just apply a voltage at very, very low frequencies and try to look at this attenuation, sorry, I'm not doing a good job of this.
Maybe I'm guessing that it was just a question of expressing it. It's clear that this that there is already a breaking of the symmetry, right-left symmetry or parity, is in the fact that this wave is traveling in one direction.
Correct.
Already minus sign in the cosine is already breaks that symmetry, right?
Right. So this breaks parity. I think one thing that the reason why this is the solution and not say the opposite is, but if you solve the Navier-Stokes equation with these boundary conditions that I wrote earlier, this is what you this is what you get. And there's going to be some reflected component that I've ignored here, which is going to be something like e to the minus 2 alpha, or e to the there's also an e to the minus alpha L on top of that.
Yeah. Okay. Yeah. Well, may I ask another question?
Sure.
So if we are talking about hydrodynamics in 2+1 dimensions, it has some logarithmic divergence in the definition of kinetic coefficient, including I suspect conductivity as well. Is that in any way showing up in this, or this logarithmic dependence of kinetic coefficient?
Right. So right, that doesn't, well, because of the starting point that we're starting with just I guess this, right? So you're not going to see those kind of like 2+1D log. We're starting with this Navier-Stokes description, so you're not going to see that. In principle, I think, if we were to actually do some kind of microscopic calculation, those kinds of logarithmic divergences that you would expect to see in 2+1D would be cut off by the fact that I have some finite resistivity in the sample. That length scale will probably dominate before you hit lengths long enough where the log matters.
Okay, thanks.
All right. Any other questions? Okay. So if not, I'll turn to the final proposal that we have, which is known as Rayleigh streaming. And so the previous, the Eckart streaming and the Rayleigh streaming go under this kind of blanket category called acoustic streaming. And this Rayleigh streaming actually is probably it is the first one studied way back in like the late 1800s. So as opposed to the previous Eckart streaming section, which was focused on bulk dissipation, here we're going to focus primarily on, or only on boundary dissipation. So we're going to imagine setting up a standing wave in the same type of rectangular geometry, and this time no bulk attenuation. And we're going to also enforce that the DC current through the device is 0. And this is just a technical, this just makes life easier, and it kind of removes the previous DC current effects that we saw in Eckart streaming to really isolate the Rayleigh streaming effect. Now, this finite, there's a finite width h with no slip boundary conditions in the y direction, meaning that the velocity has to vanish at the walls here. But clearly this standing wave solution does not do that. It has no y dependence. So what you need to do is to correct for this with a transverse velocity component, a VT here. And this is what accounts for this boundary dissipation. And so we can run the same game by calculating the DC convective force based on this first order velocity. And again, we find that it's non-zero. This time the functional form is quite a bit different. There are two features, namely one being an exponential decay from the wall, and then the second, this halved period compared to the sine kx that we had before. And this is just from the fact that it's v squared nonlinearity. This exponential decay from the wall comes from a similar reason as the convective force from before, and it's namely that all the dissipation is isolated and exponentially localized to the walls, and this, which comes from this VT term. So what I want to convince you is that this convective force will end up leading to these circulating cells of current, where you have this repeating patterns of up sense and down sense, just repeated indefinitely as with the size of your device. Okay, so to understand how this effect comes about, we're going to split our device into two regimes, a bulk and a boundary layer, based on the strength of the convection force, the DC convection force. So in the boundary layer regime, where the DC convective force is non-zero, you, as before, solve and you find that the velocity is going to be non-zero, being pushed along by this convection. So at the edge, you have no slip, so velocity is zero, and then it increases as you go away from the wall. And it terminates at the bulk boundary interface at some v slip, some slip velocity. And so what makes this kind of interesting and kind of surprising to us at first was the fact that even though one might naively expect that nothing interesting can happen in the bulk because there's no force, actually because the convection force is non-zero in the boundary layer, this information is actually not isolated to the boundary layer, but actually propagates up into the bulk. And so, so then when you solve the bulk equations, because there's some current here at the bulk boundary interface, if you combine this fact with current conservation and total DC current zero, any current that goes to the left must circulate back around. Right? And so you'll generate these current loops. Right. And so now that you have current loops, you can ask about, what is the magnetization of the sample based on these current loops, and is it a measurable magnetic field, and things like that. So to estimate this for graphene, again, we're taking frequency 2 terahertz, and then you'll see DC magnetic fields on the order of 10 to the minus 10 Tesla for 9.3 microamps of input current amplitude, magnetometer 1 micrometer away. So probably measurable with a scanning squid, hopefully. So yeah. So with that, I'd just like to, I guess, conclude and summarize, and then take any questions. Just, I guess I tried to argue at the beginning that linear hydrodynamics is phenomenologically equivalent to Ohm's law, and so it becomes difficult and pretty involved to try to distinguish which one is really hydro and which one is not. And therefore, instead, we propose to look at nonlinear hydro effects, of which we have 3. And it would be interesting to continue exploring some of these effects, or perhaps new effects that the classical literature might not have captured because we have some additional features in electron hydrodynamics. As Luca kind of pointed out earlier, there are potentially other non-linearities or other interesting features that may be present for some of these electronic hydrodynamic materials that we didn't really account for. We just took the kind of the simplest, most basic Navier-Stokes equations and just investigated what the non-linearity effects could be. And finally, it'd be interesting to kind of imagine or envision what some potential for nonlinear circuit elements some of these hydrodynamic devices could eventually become as we study some of these nonlinearities more and more, make some of these devices cleaner and cleaner. So with that, just thank you for your time and be happy to take any questions.
All right, let's thank Aaron for the nice talk. And we have time for some questions. Maybe I can start with a question. So I guess any system, whether it has a hydrodynamic regime or not, will have some version of this, right? Of nonlinear versions of Ohm's law, like a nonlinear response. If I turn on some kind of local electric field, I'll have some currents that depends on arbitrary higher point. And so in a sense, what you're doing here is you're parameterizing some of these higher, I guess, nonlinear response functions. Is that
right?
Say
that, yeah, you can think of it that way. Yeah.
So you would see them. I mean, you would expect to see them in any system, but maybe in a system that has hydrodynamics, you expect them to have a particular form.
Right. So yes, that's precisely right. In hydrodynamics, there's a natural, I guess, there's a dimensionless number which you can characterize the strength. There's a particular form of the nonlinearity that you expect, namely this v dot grad v. So of course, if you drive any system hard enough, you'll have these arbitrary nonlinear like 2-point functions or whatever, or 3-point functions, whatever. But I think I guess this is one of the questions that we were trying to think about as we were like wrapping up this is how do we actually see convection come microscopically? People talk about like the emergence of hydrodynamics from kinetic theory, and you can definitely see that there's a convection term that arises. So then the natural question to ask is, okay, what other nonlinearities can you get? Say if I have some band structure with like K4, right? How does that appear in hydrodynamics? And I think that's still something that we are looking at.
Okay, so if there are no further questions, I'll stop the recording.